Hi everyone! In this video, I'll demonstrate how to automatically analyze a single Winston-Lutz image using Python. The goal is simple. Given one EPID image, automatically determine the center of the radiation field, locate the center of the ball bearing, and calculate the Winston-Lutz offset in IEC coordinates. Why Winston-Lutz matters? The Winston-Lutz test is one of the most important quality assurance procedures in stereotactic radiotherapy. Its purpose is to verify the coincidence between the radiation isocenter and the mechanical isocenter. As treatment techniques such as SRS and SBRT demand sub-millimeter accuracy, even very small deviations can become clinically important. Although many commercial solutions exist, the underlying image processing is actually quite elegant and makes an excellent programming exercise. The input. For this demonstration, I'm using a synthetic DICOM image that mimics a real EPID acquisition. The image contains a 2 by 2 cm radiation field, a 5 mm ball bearing, some realistic epic blur and noise, and a known geometric offset. Using a synthetic image allows us to know the exact ground truth while avoiding the use of any clinical data. Step 1. Read the DICOM. The first step is reading the DICOM image using pydicom. After loading the pixel data, the image is normalized to improve numerical stability. A small Gaussian filter is then applied to reduce image noise before performing feature detection. Step 2. Locate the ball bearing. Since the BB appears as a dark object inside the radiation field, we invert the local intensity within a small region around isocenter. This converts the BB into a bright Gaussian-like signal. Instead of simply selecting the darkest pixel, we fit a two-dimensional Gaussian model. Gaussian fitting provides subpixel localization, allowing the BB center to be estimated much more accurately than the detector pixel spacing. So this part is to detect the BB. Step 3. Locate the radiation field. Next, we determine the radiation field center. The image is inverted and thresholded to isolate the radiation field. Morphological closing removes small imperfections. OpenCV is then used to identify the largest contour. A minimum area rotated rectangle is fitted to that contour, providing the field center as well as the field orientation. This will be useful when we deal with collimator rotations in the future. Step 3. Calculate the Winston-Lutz offset. Once both centers have been identified, the offset calculation becomes straightforward. The difference between the BB center and the field center is converted from pixels into millimeters using the detector pixel spacing, which can be extracted from the DICOM header, or you can also input the pixel spacing manually if needed. The result is then reported in IEC coordinates as DU and DV. This represents the translational offset measured in the image plane. So now let's run it. It will analyze this synthetic 004 image. As it runs, it will first print an image for our visualization. The green circle represents the center of the BB, and the red circle represents the center of the detected radiation field. Then it will report the offset in the DU-DV direction. And this is consistent with our ground truth when we generate the synthetic image. Current scope. It is important to know that this program analyzes only one single EPID image. At this stage, we are measuring the two-dimensional offset within one projection. While this is already useful for understanding the image processing workflow, a complete Winston-Lutz analysis requires information from multiple images acquired at different machine angles. In upcoming videos, we'll extend this framework considerably. Instead of analyzing a single image, we'll incorporate the acquisition geometry, including gantry angle, collimator angle, couch angle, and combine measurements from multiple Winston-Lutz images. Using those acquisition angles, together with the measured DU and DV values, we'll reconstruct the three-dimensional radiation isocenter deviations. This moves beyond single image processing into full geometric characterization of the treatment delivery system. If you found this helpful, feel free to subscribe. In future videos, we'll continue building this Winston-Lutz analysis tool step by step. You can grab the Python script for both analyze single image and the synthetic generator in the descriptions. Thank you for watching, and I'll see you in the next video. Bye!